Hello world, it's W3 here. Welcome back to the channel. In today's tutorial we are going to go over Linux kernel modules, more specifically kernel rootkits. So before I start, I'm actually going to show you some functionality of a rootkit I've been working on personally and show you some cool things that it's able to do. So I'm going to go into my VPS, going to zoom in so you can see a bit more. I'm going to cd into my rootkit folder. I'm going to do ls. So we've got a make file here. I'll explain that a little bit later. But basically, we're going to insert our rk.ko, our kernel module. And as you can see here, we've got a w3 hack file. Now, my kernel module has hooked gitdents64 and gitdents, which is git directory entries, which is what ls and other programs use basically. And I've also hooked the Syscall kill. So when I insert my kernel module, I have a magic prefix which is w3 hack. So any file that begins with w3 hack will be hidden because I've hooked the gitdents Syscall, and it will hide it. But before we load the kernel module, let's do ls mod. And we can see all the Linux kernel modules that are already in our kernel. And as we see, it starts with xt owner. We have the size, and then we have used by. So some more information. So let's clear that. Let's insert mod. I'm also going to do dmessage. And that's clear. I was going to just do clear just to clear it so it's easier to read. So let's do ins mod rk.ko. Now if we do ls mod, we can see that our kernel module has now been inserted, has been loaded, RK, that's cool. Now if we do ls, we can see that w3 hack file has disappeared because of the functionality I put into the hooked Syscall. If we do ls grep w3 hack, it's not there. If we do find dot for this directory dash iname, so the name, doesn't matter if it's capitals or not, w3 hack, it's not there. Let's do dmessage, zoom in a bit more. If we do dmessage, we can read the kernel messages, and obviously we're printing some messages ourselves. So at the beginning we've got rootkit init, so it initializes. Now we've also got original gitdents64, original gitdents, and original kill. Table entry successfully stored. So yeah, we're finding the Syscall table, we're indexing it to certain Syscalls, and then we are actually storing the addresses of those Syscalls for later. The reason for doing that is so that when we hook it, when we overwrite the table with our own hacked gitdents and kill and so on, we can do our own functionality, and then we can also call the original Syscall function so that no one is any the wiser that anything's wrong. And also because when we remove the Linux kernel module, when we want to remove it, we will also then overwrite the Syscall tables with the original gitdents addresses as well. So as you can see, we've got the original entries stored. We then unprotect memory. Now the reason we have to do this is because they've actually they've made it so that the Syscall table is like read only, you can't write to it. So we've got to do some assembly stuff, very easy, just copy and paste to unprotect the memory. We then store our own Syscall function addresses in the table, then we protect the memory again. So now when the hooked gitdents Syscall is called, I have it print it just so I can see that it's actually, it's getting called, it's going through my hacked gitdents Syscall, etc. So when I do ls, it will also print out the w3 hack file if it's on the file system, and of course it hides it as well, which we will look into a bit more later. We also have the hacked kill Syscall, so that's cool. So ls, yeah, no w3 hack file is there. I've also hooked the kill Syscall. Now kill doesn't necessarily mean just kill a program. The -9 is actually what kills your process. Kill is actually just a signal program. So you can do any signal from, say, 1, you could do 3, they all mean different things. -9 is what kills a process. Now on a 64-bit system, I think Syscall that kills from 32 to 64, you could overwrite because they're not really used often or probably at all. So I've overwritten Syscall 64 to do something, as you'll see in a minute. Now you can use any process ID because the kill Syscall, when it finds 64 or any number that we have said to look out for, it will do our functionality and then it will just return. It won't call the original Syscall because we don't want it to do anything on a process ID, because we have to give a process ID. So we can just do kill and then 1, and I do dmessage, and as you'll see down here, signal 64 equals sig super. So sig super is equal to 64 basically, and that will make us become root. Obviously it doesn't at the minute, it just prints that, but you know, it can do if you write the function for it. So if we clear that, we do kill -63 and then any process ID. Now let's check the messages. This signal 63 is equal to sig invis, which is 63, which will hide itself, the malware, etc. So you can send a signal 63 to hide all your files that belong to the rootkit, the malware, and all that stuff, etc. You can make it do whatever you want basically. So our W3 hack file is not here. We're going to remove the Linux kernel module now by doing rm mod and then rk ko again. So we'll do ls mod, and if we look at the top here, our module has disappeared now. It's not in there. That's good. If we do dmessage, we can see we've got rootkit exit, which is what I'm printing, as you'll see further on in the tutorial. We unprotect the memory again. We then restore the original syscalls into the Syscall table entries, which is why we saved them earlier as well, not just to use but to obviously put back, and then we protect the memory again. So if we go ls, we can see that we've got W3 hack file appears now. It's not hidden to the user. ls grep W3 hack, yep, find dot iname W3 hack, yep, it's found. So rootkits are actually really useful, and you can do some really cool things with them, and they're really hard to spot because obviously you can hide files, you can play magic tricks on the user because you're so low into the system. You're actually hooking syscalls, which is what, you know, programs use basically at the end of the day. So what we are going to do now is we're going to go to our text editor, and we are going to create a basic template that all Linux kernel modules need and use, and drivers, etc. We're going to do that, and then we're going to look for the Syscall table and we're going to hook into it. So let's begin with that. So we are in our text editor now, and we are going to create the basic template of what an LKM needs, Linux kernel module. Now I will say before we start, you don't really want to run the Linux kernel modules or do stuff with the kernel on your own system. You want to use, say, a VPS, etc., because if you make a mistake you can end up bricking the system, which I did a few times when I was doing this myself starting off. So if you have a VPS, it doesn't matter, you can just obviously go to the control panel in the URL and just restart the VPS. It's not a problem. Now I'm on Microsoft Azure. They have VPSs for say £5, $5. They're cheap. I use a £20 one myself, but anyone will do, to be honest. I also use Win SCP to transfer the files to the VPS, and then I can run it in the terminal, etc. So to begin, I'm just going to copy and paste these 3 lines here. So let's just copy and paste these three modules here first of all, because we're going to need them. So we've got these three includes. We've got linux/init.h, which contains macros used to mark up functions, e.g. __init__exit. You'll see more about that in just a minute. We've also got Linux module.h, core header for loading LKMs into the kernel, and we've also got linux/kernel.h. Now this contains types, macros, functions for the kernel, e.g. kern_info, kern_error, etc, etc. So we'll see more of that in just a second as well. Now, when you are creating a Linux kernel module, or LKMs, you cannot include user space libraries. So for instance, in a normal user space program, you would say include stdlib.h or include stdio.h. We cannot use these in a Linux kernel module. We have to actually use kernel, specifically kernel module, kernel includes, kernel libraries only. So yeah, we have these three here. All LKMs will need these three headers, 100%. So to start off with, in a user space program, it starts with say int main, and then so on as void say, and then like that. Now user space program will start at the main function here. A Linux kernel module doesn't do that, so we have to do static, and then we got int, so that means just the type we are returning will be an integer. Now ints are obviously 4 bytes long as well. Static int. The static word here means that this function's user space say will be in just this file, which means no other Linux kernel modules or no other files can actually call this function. This function can only be used in this file. The reason for doing that is because all Linux kernel modules and the kernel, they're actually just one whole program. So you might get conflicting names and so on and so forth. So we use static, as that obviously helps. So we've got static int, and now we're going to do __init. So this is where the linux/init.h header comes in. Macros used to mark up functions. So we're using the init macro to mark up this function. Now we're going to name the function. I'm going to just call it mod_init, and then we're going to put void. So we're taking no arguments, and then brackets, and I'm just going to return 0. We are returning 0 because we've told it that we are going to return an integer. Returning 0 obviously means that this function, there was no errors basically as well. So yeah, mod_init is just standing for module initialize or something like that. You can name it whatever you like basically. Now we're also going to do static void, so we're going to return nothing, and we're going to do __exit, and then mod_exit, and we're also going to do void for the arguments. Doesn't take any arguments. So these are the two functions that you need when you create a Linux kernel module or a driver, etc. You need the init module and the exit. This function will run when you insert your module, and this function will run when you exit your module. But we also need two other things as well. We need to do module_init, and we need to put our function in there, so mod init, and we can do module_exit, and then our module exit. So this function here is what will load our initializing function, and this module_exit will load our exiting function when we remove the module, for instance. Now, so this is a basic setup of a Linux kernel module. So what we can do now is we can print some information that we can view when we do dmessage command, or we look into the kernel log. So in C, you would do printf, but obviously we're not in user space, so we cannot use printf and we cannot include the library for printf. But we have included Linux kernel.h, which contains types, macros and functions. So we actually have a function called printk. Now obviously printk stands for print into the kernel, and then we can do kern_info. There are other ones like kern error and other ones, but we'll just use kern_info. Now we don't use a comma like you would think and then start typing. Now obviously you may make a few mistakes with that. I did it myself. It sometimes happens, but actually it's just a space. And we're just going to put rootkit and then colon and then init. And obviously we're going to do /n as well, because if you don't put a /n and you load your kernel module and you do dmessage or you look into the kernel logs, you may not see your printk, because it will still be in the buffer and you haven't flushed it. Putting a /n at the end will flush the buffer, and actually you'll be able to see your print without having to wait until you exit. So we're going to do that. Now as well, when we use a colon like this, it will make this rootkit color come up, so it'll be colorful, so it's easier to read as well. So we'll just print k rootkit init, and on this one we're just going to print k and then kern_info rootkit exit /n. So we've got our little setup here. We save this. So now that we've got the basic setup, let's go to I'm using WinSCP to transfer files to my VPS. So I'm going to transfer the w3.c into my VPS file folder. So now I'm back on the VPS, going to do ls, and we've got w3.c. So to compile and create this Linux kernel module, we actually need a make file. So I'm going to just vim make file. So this is what you need in your make file. Now you can just literally copy and paste this and it'll be fine, but what you do need to change is the obj-m. You need to change the name of your, so whatever you've named your file that you're creating your Linux kernel module in, you have to put the name of it here. So I've named mine w3.c, so I'm going to put w3, and now I'm going to save that. And if we have a look at the make file, so we just cat make file, we can see we've got it here, and basically this is what we need to make the Linux kernel module. Simple as that. You can just copy paste it and change the name here. So we're going to run make now, and it's creating our Linux kernel module. So now if we do ls, we now have, instead of w3.c, we also have some files here called w3ko, w3o, etc, etc. Now our Linux kernel module is w3.ko. That is what we will be inserting in. So we will do that now. I'm just going to quickly have a look at dmessage. I'm going to clear dmessage by doing dmessage -- clear. So you can use dmessage to view messages to the kernel log, or we can also go to cd. Now if we do ls/et/var, and as we can see we've got a log file folder in there, so we could do ls/var/log, and then in here we have kern.log, so you can actually do cat and then var log kern.log, and we've also got some logs here as well, as we can see from before. But we'll just use dmessage, it's very easy, and I've just cleared it so we can see. So let's lsmod, and we can see our kernel module is not in there at the minute. So we'll do insmod w3.ko. Now we will do dmessage, and then we'll do lsmod to see that it's been inserted, and we've got w3. Nice. So let's do dmessage, and as we can see, we've got w3 module license unspecified taints kernel, disabling lock debugging due to kernel taint. Yep, there is a way to get rid of this, and I'm going to show you that after. But we've got our rootkit -- init, and then if we do rmmod w3.ko and we do dmessage, we've got rootkit and then exit. So we have actually printed our messages, and we have actually ran our init and exit. So that's good. You know, we're making a start. So now we've got some sort of error message looking type things here about module license, etc., etc. The way to get around this is to actually use a module license of GPL, which apparently a lot of unscrupulous module developers are using, and they don't like it. But it doesn't matter, we'll just use the license GPL, and that gives us some benefits basically. So if we go back to the Visual Studio or your text editor, and then we're going to create our what's that, lsmod. Yeah, we have actually removed it, that's all good. Okay, so now we can do so basically I'm going to copy and paste this in here. So we've got module information, so we can give it a module underscore license, and we're going to use GPL. Now using GPL gives you access to certain functions, certain functionality, and so on, and also it doesn't give you those sort of error messages per se, because you've got a license of GPL. You can look into it more yourself, but yeah, we use GPL. Then we're also going to just give it a module author, module description, and the module version. Pretty self-explanatory, pretty simple. But yeah, we're going to give it this information. So now that we've given it a module license and some description and version and author, etc., but mainly the license, that's very important. If we save that and then we transfer the file, the new file, to the VPS, and now if we remake that file by doing make, then we clear that, and then if we do dmessage -- clear to clear previous messages. Now then, when we insert this module by doing insmod w3.ko, we will not get that message from before. So we do dmessage, and now we've just got rootkit in it. There's no sort of error or lock-in and so on and so forth, because we're under the guise of the GPL license. Haha. So we can do rmmod and then w3.ko to remove it, and rootkit exit. Nice and easy, good stuff. So this is the basic sort of template that you need when you create a LKM Linux kernel module, driver, rootkit, etc. So now we are going to want to find the Syscall table, and yeah, so let's go and look for the Syscall table. Okay, so we want to get the Syscall table basically. That'll be the start of the Syscall table, and then we can index the Syscall table, as you'll see in a minute. So there's many ways to get the Syscall table depending on your Linux kernel version. Okay, now I'm going to show you, obviously, in the VPS there's actually a file. This file is not on all distros because it has been taken off, because they're trying to stop people from actually, you know, creating rootkits and hooking syscalls and so on. So there are some protections, but we can get around it relatively easy. But if we just look in ls/proc, we can see it has lots of files, and it has a file here called call all sims, which is basically kernel all and then symbols. So if we were to cat/proc/k all sims, we'll see we've got many kernel symbols here. Now I'm just going to stop that. So if we do cat and then /proc/kall sims, and then we grep for sys_call_table, you'll see that we actually find the address for the syscall table. Now this address changes each time, so we cannot just copy an address and just use it. And also we can do cat/proc/call sims, and then we can grep, and then we can do kall sims_lookup_name, and we found this also. Now call sims_lookup_name is actually a function in the Linux kernel which is used to look up system call names, and if it finds it, it will return the address for that system call, and if it doesn't, it returns let's have a look quick. If we Google call sims_lookup_name, we go down and you'll find a website that looks like a lot of to do with, say, Linux kernel modules and rootkits especially, is actually just looking into the kernel and reading documents, and getting a better understanding of the kernel basically. But we have a callsims.c file, and this file contains lots of functions for call sims expand symbol, blah blah blah. But if we look for kall sims_lookup_name, we'll see it brings us to this function, and we've actually got a comment here which says look up the address for this symbol, returns 0 if not found, and we have to give it a value of const_char pointer and then name. So we give it a value of const_char pointer, so that's basically a string. So we can give this function a string, and if it finds that symbol, e.g. say the syscall table, it returns the address for that table, where that is basically in memory, and if it doesn't find it, it returns a 0. So we can actually use this to find the syscall table. We can point to it, and then we can index the syscalls, as you'll see later on. Now we could use this, but it's not really very good because obviously this is in user space and we cannot just point to memory in user space and so on. So we would have to actually create a user space program or script to get this and then put it into a user space buffer, and then we'd have to actually copy the data from that user space buffer into a kernel space buffer that we've created, and there's just really no point when we've actually got a function we can use anyway. Now in some versions that function may not exist, but on Ubuntu it does, and we can use it for now, and yeah, it's pretty good. But I was just showing you how there is actually a call sims file in proc and so on. So we're going to use this function here to grab the syscall table. So we'll just clear that and we'll go back to here. Now if we look at the I'll zoom in a bit. If we look at the function for the call sims_lookup_name, it will return an address, and the type it returns is an unsigned long. So we want to create a variable, so we're going to do unsigned long. We're going to make it a pointer because we want to get this address for the syscall table. When we put syscall table here, we want to get that address, but we want it to be a point. We want to be a pointer. We want to point to that address, and then we can move the pointer through the memory to certain syscalls, etc. So we're going to do unsigned long pointer, and then we'll just do __sys_call_table, and we'll put that to null. Now null is actually null is a void pointer, so null is equal to void pointer 0. So it's equal to the value 0, and then we're typecasting it to a void pointer, and that's what null is anyway. Null does that anyway, implicitly does that, so that's fine to do. And a void pointer is implicitly typecast to the type that it is being assigned to. So we've got unsigned long pointer here. Null being a void pointer 0 will be typecast to unsigned long pointer 0. Okay, just for your reference. Obviously you may not know some of this because it's C. Most of my videos are Python, but obviously, you know, spend a bit of time learning. You're not meant to get it straight away. It does take a bit of time, and that's totally fine. So we've got our Syscall table variable, which is unsigned long, and it's a pointer. So what we can do is we are going to import, we're going to include linux / and then kallsims.h. So this will give us basically callsims lookup name, because if we open this into a new tab, we can see that actually that is defined in one file as a prototype, which is callsims.h. So we import callsims.h, and we get all these functions basically, or many of them most likely, and we can use callsims_lookup_name. So we import that. So this callsims.h contains functions, e.g. the kallsims kernel or symbols _lookup_name. So we include this header because if we look at the kallsims.h, it's got a prototype here for callsims_lookup_name, and it returns an unsigned long, which will be of the address. So now that we've included this library, we can go down here. We can use our pointer _sys_call_table, and so we can do _sys_call_table equals, and then we can do kallsims_lookup_name. Now the arguments it takes is a const char pointer, so it takes a string. We can give it a string, and the name of the symbol we want is the sys_call_table. Now this here, sys_call_table, this will return the address of the syscall table. This is the starting position. This is the starting point of the syscall table. So if we point to that address in memory, we can then index that memory to find obviously the syscall table, the syscalls that we want to hook and store and so on. So we're just pointing to the start of the syscall table, which holds all the syscalls that we want to use. Now we can't just leave it like this, because otherwise you're going to get an error, because remember, callsims lookup name returns a unsigned long, as we can see here, unsigned long, but it is returning the address of the syscall table. So we've got a pointer here, which is unsigned long pointer. So what we're going to do is we're going to typecast it to unsigned long pointer like that. So now we won't get any errors. We've typecasted it. Now that's all good. So now our sys_call_table is pointing to that location in memory, and then we can actually index this syscall table. We can move the pointer forward certain amount of bytes and so on to index certain memory addresses, which is going to be certain syscalls and so on and so forth. So now we've actually got the syscall table, and that's good. Let's run it and see if we get any errors. So we'll save that, and then I'm going to transfer the new file over to the VPS. That's all good. And then we've got a CD into the right folder. So we're going to do make again to make the file. No errors, all good. We'll clear the message and then we'll insert our mod w3.ko. So let's look at the message. We've got rootkit in it. We'll remove the mod w3.ko. So we've got no errors when compiling and no errors in the kernel messages. So that's all good, works well and very good. So now if we want to index the syscall table to certain syscalls, we have to include another header, which is going to be include linux / and then uni std.h. Now this header include, there we go. So this header contains syscall names to numbers. It basically just contains the syscall numbers basically. We save that, and if we were to Google linux / uni std, we've got a file here, and as you can see the syscalls are defined. We've got __nr_ and then restart syscall, and it's defined as a number. And then we've got define __nr_ kill is defined as the number 129. So we've imported this header, and then when we want to index our syscall table, instead of using a number, which could change in different versions and that, it could change, but the name will still remain the same. So what we can do is we can actually include a Linux / version header, because obviously different versions have different sort of ways you have to get the syscall table, different syscall hooks and so on. So we can copy and paste this in here, linux / version.h, and it's linux / kernel versions, e.g. linux _version _code and kernel _version. What we can also do as well is we can create a function, so static, and it can return an integer, and we're going to say get _syscall _table. It's going to take in void arguments, no arguments, and it's going to return 0. So in our syscall, in our get _syscall table, we can create a variable, a unsigned long pointer, syscall _table. So we can create a pointer, because obviously this here takes a pointer. So we can delete this here now, and we can also delete this. So we create a pointer, syscall _table. And then we're going to do a if directive. It's a pre-processor directive. So okay, so I will paste this in here. It's a comment. It's if linux _version _code is greater than kernel _version 4.4.0. then we can obviously do the method that we would used to do it just a minute ago. So we can do hashtag, and then we can do if, so preprocessor directive, if Linux _version _code is greater than kernel _version 4.4.0. So if the Linux version is greater than 4.4, we can then do, I'll paste this in here. So we've got syscall _table, so which is our pointer, equals, and then call sims _lookup _name, the syscall table, and then we are typecasting it to an unsigned long pointer, which is what we did down here just a minute ago, but we're putting it into a function now. And then what we can do is we can just we can return syscall _table, and it's returning a unsigned long pointer, so we'll make the return type unsigned long pointer like that. So our function get underscore syscall underscore table will now check if it's a certain version, and if it is, it will then do this version. And then obviously there are other versions that you can you have to do other stuff, but I'm not going to go into that in this video. But we'll just create the function anyway, so it's there if you wanted to add it on later and so on. So we return the syscall table, and now what we can do in our init, our mod init function, is we can do underscore underscore sys underscore call underscore table equals, and then we can do get underscore sys call underscore table, just like that, because this will return a unsigned long pointer which is equal to our call sims lookup name syscall table. So that's all good. You can save that, and very nice. That is going to be the end of part 1. So I hope you enjoyed the video. It's probably going to be quite a long one, I know, but there's quite a lot of information that you need to sort of know when making these LKMs and that. So I've tried to explain it the best I can. In the next part 2, we're going to store some syscalls, and we are going to unprotect the memory, protect the memory, and then we're going to create a hook. So we're going to create a hacked syscall, and then we're going to hook the syscall table, run the LKM, and see our syscall being hooked and printing our message, and so on. So I hope you enjoyed the video. Well done for getting to the end if you did, and I'll see you in the next one. Goodbye.
Como tú, teta hecha, culo hecho y actitud. Hoy te voy a buscar, ponte la mini, que te lo meto en el Lamborghini. Trépate encima de mí, y ni yo la quiero como tú. Teta hecha, culo hecho y actitud. Hoy te voy a buscar, ponte la mini, que te lo meto en el Lamborghini. Y ni yo la quiero como tú. Teta hecha, culo hecho y actitud. Hoy te voy a buscar, ponte la mini, que te lo meto en el Lamborghini. Trépate encima de mí, baby, yo la quiero como tú. Teta hecha, culo hecho y actitud. Hoy te voy a buscar, ponte la mini, que te lo meto en el Lamborghini. Trépate.